Part 2, Warming Up with Calculus Prerequisites. In this part, Algebra Review. Richard Feynman, the great 20th century physicist, said, tongue-in-cheek, that calculus was the language that God spoke. Well, I don't know about that, but I do know that algebra is the language of calculus. If you want to learn calculus, you've got to know your algebra. Logarithm review. What's log 10? And ln1, hint for the first one, it's the loneliest number. Hint for the second, there's nothing to it. Function review. Even and odd functions, exponential functions, inverse functions, function transformations, and so on. Some trig, the all-important unit circle, and the related geometry of the 30, 60 degree, 90 degrees, and 45 degree to 45 degree and 90 degree triangles. More trig, SOHCAHTOA, and the graphs of sine, cosine, and tangent. Chapter 4, Algebra and Algebra Review. In this chapter, winning the fraction battle, divide and conquer, boosting your powers and getting to the root of roots, laying down the laws of logarithms and having fun with factoring, hanging around the quad solving quadratics. Algebra is the language of calculus. You can't do calculus without knowing algebra any more than you can write Chinese poetry without knowing Chinese. So, if your pre-algebra and algebra are a bit rusty, you know all those rules for algebraic expressions, equations, fractions, powers, roots, logarithms, factoring, quadratics, and so on, make sure you review the following basics. Fine-tuning your fractions. Open a calculus book to any random page, and you'll very likely see a fraction. You can't escape them. Dealing with them requires that you know a few rules. Some quick rules. First is a rule that's simple but very important because it comes up time and time again in the study of calculus. You can't divide by 0. The denominator of a fraction can never equal 0. 0 over 5 equals 0, but 5 over 0 is undefined. It's easy to see why 5 over 0 is undefined when you consider how division works. 8 over 2 equals 4. This tells you, of course, that 2 goes into 8 4 times. In other words, 2 plus 2 plus 2 plus 2 equals 8. Well, how many zeros would you need to add up to make 5? You can't do it, and so you can't divide 5 or any other number by 0. Here's another quick rule. Definition of reciprocal. The reciprocal of a number or expression is its multiplicative inverse, which is a fancy way of saying that the product of something and its reciprocal is 1. To get the reciprocal of a fraction, flip it upside down. The reciprocal of 3 over 4 is 4 over 3. The reciprocal of 6, which equals 6 over 1, is 1 over 6. The reciprocal of x minus 2 is 1 over x minus 2. Multiplying fractions. Adding is usually easier than multiplying, but with fractions the reverse is true. So I want to deal with multiplication first. Multiplying fractions is straightforward. Just multiply straight across the top and straight across the bottom. 2 over 5 times 3 over 4 equals 6 over 20. A over B times C over D equals A times C over B times D. Dividing fractions. Dividing fractions has one additional step. Flip the second fraction and then multiply like this. 3 over 10 divided by 4 over 5. Rewrite as 3 over 10 times 5 over 4. This equals 15 over 40. Now cancel a factor of 5 from the numerator and denominator. The result is 3 over 8. Note that you could have cancelled before multiplying, because 5 goes into 5 one time and 5 goes into 10 two times, you can cancel a factor of 5. 3 over 10 times 5 over 4 equals 3 over 8. Also, note that the original problem could have been written as 3 over 10 divided by 4 over 5. Adding fractions. You know that. 2 over 7 plus 3 over 7 equals 5 over 7. You can add these up like this because you already have a common denominator. It works the same with variables. A over C plus B over C equals A plus B over C. Notice that wherever you have a 2 in the top equation, an A is in the bottom equation. Wherever a 3 is in the top equation, a B is in the bottom equation, and ditto for 7 and C. This illustrates a powerful principle. Variables always behave exactly like numbers. If you're wondering what to do with variables in a problem, ask yourself how you would do the problem if there were numbers in it instead of variables. Then do the problem with the variables the same way, like this. A over B plus C over D. You can't add these fractions like you did in the previous example because this problem has no common denominator. Now, assuming you're stumped, do the problem with numbers instead of variables. Remember how to add 2 over 5 plus 3 over 8. I'm not going to simplify each line of the solution. You'll see why in a minute. 1. Find the least common denominator. Actually, any common denominator will work when adding and convert the fractions. The least common denominator is 5 times 8, or 40, so convert each fraction into 40ths. 2 over 5 becomes 2 times 8 over 5 times 8. 3 over 8 becomes 3 times 5 over 8 times 5. Thus, 2 over 5 plus 3 over 8 equals 16 over 40 plus 15 over 40. Note, 8 times 5 equals 5 times 8, so you can reverse the order. These fractions are 40ths, but I want to leave the 5 times 8 in the denominators for now. 2. Add the numerators and keep the common denominator unchanged. 16 plus 15 over 40 equals 31 over 40. Now you're ready to do the original problem, a over b plus c over d. In this problem, you have an a instead of a 2, a b instead of a 5, a c instead of a 3, and a d instead of an 8. Just carry out the exact same steps you do when adding 2 over 5 plus 3 over 8. You can think of each of the numbers in the above solution as stamped on one side of a coin with the corresponding variable stamped on the other side. For instance, there's a coin with a 2 on one side and an ak on the opposite side. Another coin has an 8 on one side and a dik on the other side, and so on. Now, take each step of the previous solution, flip each coin over, and voila, you've got the solution to the original problem. Here's the final answer. A times d plus c times b over b times d. Subtracting fractions. Subtracting fractions works like adding fractions, except instead of adding, you subtract. Insights like this are the reason they pay me the big bucks. Cancelling in fractions. Finishing calculus problems, after you've done all the calculus steps, sometimes requires some pretty messy algebra, including cancelling. Make sure you know how to cancel and when you can and can't do it. In the fraction x to the power of 5 times y squared over x cubed times z, 3 sure x's can be cancelled from the numerator and denominator, resulting in the simplified fraction x squared times y squared over z. If you write out the x's instead of using exponents, you can more clearly see how this works. X to the power of 5 times y squared over x cubed times z equals x times x times x times xx times xy y over x times x times x times z. Now, cancel 3 x's from the numerator and denominator. That leaves you with x times y over z, or x squared times y squared over z. Express yourself. An algebraic expression, or just expression, is something like x times y times z, or a squared times p cubed times the square root of q minus 6. Basically, anything without an equal sign. If it has an equal sign, it's an equation. Cancelling works the same way with expressions as it does for single variables. By the way, that's a tip not just for cancelling, but for all algebra topics. Expressions always behave exactly like variables. So if each x in the preceding problem is replaced with x times y times z minus q, you've got x times y times z 5 times y cubed over x times y times z minus q cubed times z. 3 of the expression x times y times z minus q cancel from the numerator and denominator, just as the 3 x's cancelled. The simplified result is x times y times z minus q squared times y squared over z, the multiplication rule for cancelling and ln. Now you know how to cancel. You also need to know when you can cancel. The multiplication rule, you can cancel in a fraction only when it has an unbroken chain of multiplication through the entire numerator and the entire denominator. Cancelling is allowed in a fraction like this: a squared b cubed xy minus pq to the 4th power c plus d over a b to the 4th power z xy minus pq cubed. Think of multiplication as something that conducts electricity. Electrical current can flow from one end of the c plus d numerator to the other, from the to the, because all the variables and expressions are connected with multiplication. Note that an addition or subtraction sign inside parentheses, the plus sign in, for instance, doesn't break the current. Because the denominator also has an unbroken chain of multiplication, cancelling is allowed. You can cancel 1a, 3 b's, and 3 of the expression xy minus pq. Here's the result: axy minus pq c plus d over bz. When you can't cancel, but adding an innocuous-looking 1 to the numerator of the original fraction changes everything. A squared b cubed xy minus pq to the 4th power c plus d plus 1 over ab to the 4th power z xy minus pq cubed. The addition sign in front of the 1 breaks the electrical current, and no cancelling is allowed anywhere in the fraction. Absolute value, absolutely easy. Absolute value just turns a negative number into a positive and does nothing to a positive number or 0. For example, the absolute value of -6 is 6, the absolute value of 3 is 3, and the absolute value of 0 is 0. It's a bit trickier when dealing with variables. If x is 0 or positive, then the absolute value bars do nothing, and thus the absolute value of x equals x. But if x is negative, the absolute value of x is positive, and you write the absolute value of x equals negative x. For example, if x equals -5, the absolute value of -5 equals negative of -5, which equals 5. Negative x can be a positive number. When x is a negative number, negative x read as negative x, or the opposite of x, is a positive. Empowering your powers. You are powerless in calculus if you don't know the power rules. X raised to the 0 power equals 1. This is the rule regardless of what x equals, a fraction, a negative anything, except for 0. 0 raised to the 0 power is undefined. Let's call it the kitchen sink rule, where the kitchen sink represents 0. Everything but the kitchen sink raised to the 0 power equals 1. X raised to the -3 equals 1 over x raised to the 3rd power, and x raised to the -a equals 1 over x raised to the a. For example, 4 raised to the -2 equals 1 over 4, raised to the 2nd power equals 1 over 16. This is huge! Don't forget it. Note that the power is negative, but the answer of 1 over 16 is not negative. X raised to the 2/3 equals the cube root of x squared, and x raised to the a over b equals the bth root of x raised to the a equals the bth root of x raised to the a. You can use this handy rule backwards to convert a root problem into an easier power problem. X squared times x cubed equals x raised to the 5th power, and x raised to the a times x raised to the b equals x raised to the a plus b. You add the powers here. By the way, you can't do anything to x squared plus x cubed. You can't add x squared to x cubed because they're not like terms. You can only add or subtract terms when the variable part of each term is the same. For instance, 3 times x times y squared times z plus 4 times x times y squared times z equals 7 times x times y squared times z. This works for exactly the same reason. I'm not kidding. That 3 chairs plus 4 chairs is 7 chairs, and you can't add unlike terms, just like you can't add 5 chairs plus 2 cars. X raised to the 5th power over x raised to the 3rd power equals x squared, and x squared over x raised to the 6th power equals x raised to the -4, and x raised to the a over x raised to the b equals x raised to the a minus b. Here you subtract the powers. X squared raised to the 3rd power equals x raised to the 6th power, and x raised to the a raised to the b equals x raised to the a times b. You multiply the powers here. X times y times z. Raised to the 3rd power equals x cubed times y cubed times z cubed, and x times y times z raised to the a equals x raised to the a times y raised to the a raised to the a. Here you distribute the power to each variable. X over y raised to the 4th power equals x raised to the 4th power over y raised to the 4th power, and x over y raised to the a equals x raised to the a over y raised to the a. Here you also distribute the power to each variable. X plus y squared equals x squared plus y squared. Do not distribute the power in this case. Instead, multiply it out the long way. X plus y squared equals x plus y times x plus y x squared plus x times y plus x times y plus y squared equals x squared plus 2 times x times y plus y squared. Watch what happens if you erroneously use the preceding law with numbers. 3 plus 5 squared equals 8 squared, or 64. Not 3 squared plus 5 squared, which equals 9 plus 25, or 34. Rooting for roots, especially square roots, come up all the time in calculus. So knowing how they work and understanding the fundamental connection between roots and powers is essential. And of course, that's what I'm about to tell you. Roots rule make that root rules. Any root can be converted into a power. For example, the cube root of x equals x raised to the 1/3 power, the square root of x equals x raised to the 1/2 power, and the fourth root of x cubed equals x raised to the 3/4 power. So, if you get a problem with roots in it, you can just convert each root into a power and use the power rules instead to solve the problem. This is a very useful technique. Because you have this option, the following root rules are less important than the power rules, but you really should know them anyway. The square root of 0 equals 0, and the square of 1 equals 1. But you knew that, right? No negatives under even roots. You cannot have a negative number under a square root or under any other even-numbered root, at least not in basic calculus. Square root of a times square root of b equals the square root of a times b. 3 times the square root of a times 3 times the square root of b equals 3 times the square root of a times b. And n times the square root of a times n times the square root of b equals n times the square root of a times b. Square root of a over square root of b equals the square root of a over b. 3 times the square root of a over 3 times the square root of b equals 3 times the square root of a over b. And n times the square root of a over n times the square root of b equals n times the square root of a over b. 3 times the square root of 4 times a equals 12 times the square root of a. And m times n times the square root of a equals m times n times the square root of a. You multiply the root indexes. Square root of a squared equals the absolute value of a. The fourth root of a raised to the 4th power equals the absolute value of a, and the 6th root of a raised to the 6th power equals the absolute value of a. If you have an even-numbered root, you need absolute value bars on the answer, because whether a is positive or negative, the result is always positive. If it's an odd-numbered root, you don't need absolute value bars. Thus, the cube root of a cubed equals a, the 5th root of a raised to the 5th power equals a, and so on. Square root of a squared plus b squared does not equal a plus b. Make this mistake and go directly to jail. Try solving it with numbers. Square root of 2 squared plus 3 squared equals the square root of 13, which does not equal 2 plus 3. Simplifying roots. Here are 2 final things to know about roots. First, you need to understand the 2 methods for simplifying roots, like the square root of 300 or the square root of 504. The quick method works for the square root of 300 because it's easy to spot a large perfect square, 100, that divides evenly into 300. Since 300 equals 100 times 3, the square root of 100, which is 10, comes out of the root, leaving the 3 inside. The answer is 10 times the square root of 3. For the square root of 504, it's harder to find a large perfect square that divides evenly into 504. So you'll need the longer method, 1. Break 504 into a product of its prime factors. The square root of 504 equals the square root of 2 times 2 times 2 times 3 times 3 times 7. 2. Circle each pair of identical factors, circle the 2 2's, and then circle the 2 3's. 3. For each circled pair, take one number out of the square root. From the pair of 2's, take out a single 2. From the pair of 3's, take out a single 3. This leaves 2 times 3 outside the square root and 2 times 7 still inside. 4. Simplify the expression. Multiply the numbers outside the square root. 2 times 3 equals 6. Inside the square root, multiply 2 times 7, which equals 14. The final result is 6 times the square root of 14. The last thing about roots is that, by convention, you don't leave a root in the denominator of a fraction. It's a somewhat outdated and unnecessary rule, but it's still being taught. So here's how it works. If your answer is 2 over the square root of 3, you multiply it by the square root of 3 over the square root of 3. 2 over the square root of 3 multiplied by the square root of 3 over the square root of 3 equals 2 times the square root of 3 over 3. Logarithms. This is not an event at a lumberjack competition. A logarithm is just a different way of expressing an exponential relationship between numbers. For instance, 2 raised to the power of 3 equals 8, so the logarithm base 2 of 8 equals 3, written as log base 2 of 8 equals 3. These two equations say exactly the same thing. You can think of 2 to the power of 3 equals 8 as the way we write it in English, and log base 2 of 8 equals 3 as the way it might be written in Latin. Because it's easier to think and do math in English, make sure that when you see something like log base 3 of 81 equals x, you can instantly translate it into 3 to the power of x equals 81. The base of a logarithm can be any number greater than 0 other than 1. By convention, if the base is 10, you don't write it. For example, log of 1,000 equals 3 means log base 10 of 1,000 equals 3. Logarithms with base e, where e is approximately 2.72, are written as natural log instead of log base e. You should know the following logarithm properties. 1. The logarithm base c of 1 equals 0. 2. The logarithm base c of c equals 1. 3. The logarithm base c of a times b equals the logarithm base c of a plus the logarithm base c of b. 4. The logarithm base c of a divided by b equals the logarithm base c of a minus the logarithm base c of b. The logarithm base times c of a raised to the power of b equals b times the logarithm base c of a. 6. The logarithm base a of b equals the logarithm base c of b divided by the logarithm base c of a. Using this property, you can compute something like log base 3 of 20. On a calculator that only has buttons for base 10 logarithms, the log button, and natural logarithms, the ln button, by entering log of 20 divided by log of 3 using base 10 for c. On many newer calculators, you can compute log base 3 of 20 directly. 7. The logarithm base a of a raised to the power of b equals b. 8. A raised to the power of log base a of b equals b. Factoring schmactoring. When am I ever going to need it? When are you ever going to need it? For calculus, that's when. Factoring means unmultiplying, like rewriting 12 as 2 times 2 times 3. You won't run across problems like that in calculus, though. For calculus, you need to be able to factor algebraic expressions, like factoring 5xy plus 10yz into 5y times the quantity, xi plus 2z. Algebraic factoring always involves rewriting a sum of terms as a product. Here's a quick refresher course. Hashata, pulling out the GCF. The first step in factoring any type of expression is to pull out or factor out the greatest thing that all of the terms have in common. This is called the greatest common factor, GCF. For example, in the expression 8x cubed y to the 4th power plus 12x squared y to the 5th power plus 20x to the 4th power cubed at z, each term contains the factor 4x squared y cubed. So you can factor it out like this: 4x squared y cubed times the quantity, 2x squared y plus 3 squared plus 5x squared to z. Make sure you always look for a GCF to pull out before trying any other factoring techniques. Looking for a pattern. After pulling out the GCF, if there is one, the next step is to look for one of the following 3 patterns. The first pattern is extremely important, while the next 2 are used less often. Difference of squares. Knowing how to factor the difference of squares is essential. A squared minus b squared equals a minus b times a plus b. If you can rewrite something like 9x to the power of 4 minus 25 so that it looks like something squared minus something else squared, then you can apply this factoring pattern. Here's how. 9x to the power of 4 minus 25 equals 3x squared, squared minus 5 squared. Now, because something squared minus something else squared equals something minus times something plus something else, you can factor it like this. Tan 3x squared, squared minus 5 squared equals 3x squared minus 5 times 3x squared plus 5. A difference of squares, a squared minus b squared, can always be factored, but a sum of squares, a squared plus b squared, cannot. In other words, squared plus b squared is prime, meaning it cannot be broken down further. That's sum and difference of cubes. You should also know how to factor the sum and difference of cubes. A cubed plus b cubed equals a plus b times a squared minus a times b plus b squared. A cubed minus b cubed equals a minus b times a squared plus a times b plus b squared. Trying some trinomial factoring. Remember regular old trinomial factoring from your algebra days? Several definitions. A trinomial is a polynomial with three terms. A polynomial is an expression like 4x to the power of 5 minus 6x to the power of 3 plus x squared minus 5x plus 2, where, except for the constant, the 2 in this example, all the terms have a variable raised to a positive integral power. In other words, no fractional powers or negative powers are allowed. So 1 over x is not a polynomial because it equals x to the power of negative 1 ter. And no radicals, no logs, no sines or cosines or anything else, just terms with a coefficient, like the 4 in 4x to the power of 5 multiplied by a variable raised to a power. The degree of a polynomial is the polynomial's highest power of x. The polynomial at the beginning of this paragraph, for instance, has a degree of 5. It wouldn't be a bad idea to get back up to speed with problems like 6x cubed plus 13x minus 5 equals 2x plus 5 times 3x minus 1, where you have to factor the trinomial on the left into the product of the two binomials on the right. A few standard techniques for factoring a trinomial like this are floating around the mathematical ether. You probably learned one or more of them in your algebra class. If you remember one of the techniques, great! You won't have to do a lot of trinomial factoring in calculus, but it does come in handy now and then. So if your skills are a bit rusty, check out Algebra 2 for Dummies by Mary Jane Sterling Wiley, 2007. Solving quadratic equations. A quadratic equation is any second-degree polynomial equation. That's when the highest power of the variable, like x, is 2. You can solve quadratic equations by one of three basic methods. Here's method 1, factoring explained step by step. Example, solve tar 2x squared minus 5x equals 12(1). Bring all terms to one side of the equation, leaving a 0 on the other side. Start 2x squared minus 5x minus 12 equals 0, 2. Factor the quadratic equation. 2x plus 3 times x minus 4 equals 0 star. You can check the factors by multiplying them back together. Does FOIL, first, outer, inner, last, ring a bell? 3. Set each factor equal to 0 and solve using the zero product property. 2x plus 3 equals 0 or x minus 4 equals 0. Solve each equation. 9 2x equals negative 3, x equals negative 3 over 2. So the equation has two solutions. X equals negative 3 over 2 and tor x equals 4. The discriminant tells you whether a quadratic is factorable. Method 1 will work only if the quadratic is factorable. The quick test for that is simple. A quadratic is factorable if the discriminant, written as b squared minus 4ac tau, is a perfect square number like 0, 1, 4, 9, 16, 25, and so on. The discriminant is the part under the square root symbol in the quadratic formula, which will be explained in method 2. Take the quadratic equation from step 1 above. 2x squared minus 5x minus 12 equals 0. Here, a equals 2, b equals negative 5, and c equals negative 12. The discriminant b squared minus 4ac becomes negative 5 squared minus 4 times 2 times negative 12. That simplifies to 25 plus 96, which equals 121. Since 121 is a perfect square, specifically 11 squared, the quadratic is factorable. Because trinomial factoring is often quick and easy, you might choose to skip checking the discriminant and just try factoring the problem directly. But if you get stuck, checking the discriminant can save time, as it tells you whether factoring is possible. However, even if the quadratic isn't factorable, you can always solve it with the quadratic formula, which will be explained in the next section. Method 2, the quadratic formula. The solutions of any quadratic equation, ax squared plus bx plus c equals 0, can be found using the quadratic formula. X equals negative b plus or minus the square root of b squared minus 4ac all over 2a. Let's solve the same equation as in method 1 using this formula. 1. Start by writing the equation in standard form. The equation is 2x squared minus 5x minus 12 equals 0. 2. Identify the coefficients a, b, and c and plug them into the formula. Here, a equals 2, b equals -5, and c equals -12. Substitute these values into the quadratic formula. X equals -5 plus or minus the square root of -5 squared minus 4 times 2 times -12 all over 2 times 2. Simplify step by step. X equals 5 plus or minus the square root of 25 minus -96 all over 4. X equals 5 plus or minus the square root of 121 all over 4. 3. Solve for the two possible values of x. The square root of 121 is 11. X equals 5 plus 11 over 4, or x equals 5 minus 11 over 4. Simplify each. X equals 16 over 4, or x equals -6 over 4. X equals 4, or x equals -3/2. 4. Confirm your solutions. The solutions are x equals 4 and x equals -3/2, which match the results obtained in method 1. By using the quadratic formula, you'll always arrive at the correct solutions, whether or not the quadratic equation is factorable. Method 3. Completing the square. The third method of solving quadratic equations is called completing the square because it involves creating a perfect square trinomial that you can solve by taking its square root. Solve 3x squared equals 24x plus 27. 1. Put the x squared and the x terms on one side and the constant on the other. 3x squared minus 24x equals 27. 2. Divide both sides by the coefficient of x squared, unless of course it's 1. Dash x squared minus 8x equals 9. 3. Take half of the coefficient, square it, then add that to both sides. Half of -8 is -4, and -4 squared is 16, so add 16 to both sides. X squared minus 8x plus 16 equals 9 plus 16. 4. Factor the left side into a binomial squared. Notice that the factor always contains the same number you found in step 3, -4 in this example. X minus 4 squared equals 25. 5. Take the square root of both sides, remembering to put a plus or minus sign on the right side. X minus 4 equals plus or minus 5. 6. Solve. X equals 4 plus 5, or x equals 4 minus 5. X equals 9 or -1. Touch.